Hello, and thank you for joining me in 3D Caleb YouTube channel. This is 3D Caleb. I thought I'd take time to review the Raytracer code that I finished up a couple weeks ago. Somebody mentioned that they would like to have a walkthrough of the code and see how I laid it out and just kind of go through the program cats section by section and tweak things a little bit, have a little fun, and they're gonna have fun too. We can change colors, position of the lights, and things like that, and compile it. And okay, guys, compile it all, and with the Open Wacom compiler. You may notice there's no lamplight on today because it's during the day. It's lots of light coming in here. It's a snowy day. Today's a good day because Lady Luck gave me a gift, and I won $1. I got a whole $1. I'm not saying you should play scratch-off games, but you win sometimes. I don't know what I'm going to do with that yet. Or maybe I'm just going to stick it in here. So anyway, I got the code ready, cleaned it up. It's on my GitHub page, so you can see the code anytime you want. Copy it, steal it. It's all there for you. Probably should add a license. People worry about that. Put a license up there, and you can use it wherever you want. If you want to have it as a guide when you write your own Raytracer, or if you follow the computer graphics from Scratchbook. Again, I'll put that link in the description, and the link to this source code online for your pleasure. Okay, well, let's get the camera here. And I'm going to adjust the shutter speed so there's not this nasty strobing effect. So I just got to make sure shutter speed is 1/60th of a second. I think that will probably look okay. Ta-da! Hopefully you can see that okay. The shutter speed synced as good as I know how, so you don't see a nasty strobe and too much scanline junk in here. So here's the code, and you can see I tried my best here to organize it all because it is a fair amount. It's not 10 lines of code. I tried to group it up nicely, so we can start from the top here, including the typical DOS include files, and like the i86 header, the DOS header, so I can talk to the BIOS and get the mode 13H all initialized, so I can start drawing pixels to the screen like we've talked about a few videos ago. Got my handy constants like infinity and the screen width, viewport size, viewport depth, aspect ratio adjustment, because we are dealing with non-square pixels. So I actually improved the look of the sphere demo. They don't look squashed. They look more like a proper sphere. Perfect, beautiful mathematical sphere. Some other constants, calculations that I'm way kind of caching, so I don't have to do a lot of divisions, getting the pixels plotted to the viewport. And the book covers all these things. I just converted it from the pseudocode in the book to strict C89. And I'll say one thing about that, which that's kind of a pain using that old standard, or the old kind of C standard from long ago, but it works fine. We got our light definitions, we got our core data structures. You got your vector 2, your vector 3. Hopefully you know some linear algebra, how to represent points in a 2D and 3D space. We got our sphere structure, where we can contain our radius, our shininess, which is the specular, the color, which is, like it says, based on a color index of a carefully calculated color palette, and then the location of the sphere, and then we got the light, get the type, the intensity, position, direction, and then we got the really important vector operations that are add, subtract, multiply, divide, length, and dot product, and then the reflect ray, and then our graphic system here, our set mode, where we activate the right VGA mode, whether it's text mode or it's going to be 13H mode. Our ability to draw a pixel, initialize our palette, and then calculate a shade color. Then the ray tracing code, and these are just, of course, the declarations here, so you can see the API quickly. Intersect ray sphere, closest intersection, canvas to viewport. Then we have our lighting system, compute lighting, and trace ray. So those are all the declarations of these functions, and of course here's the implementation. So we have your vector add, which these are pretty easy to implement. You know, vector adding is adding two vectors together, and I decided to pass them in as a pointer to not have to have it copied the structure as you're passing it in here. Just figured this would be more efficient, but I might be wrong about that. I'm still kind of getting better at C and getting used to pointers and double pointers and, you know, referencing, and trying to get more comfortable with that. So I'm glad to be doing a lot more things in C. So I'm passing in via pointer, but there's subtract, you know, take the difference between the two vectors A and B and put it into a new result here and return it. Got our multiply, which you can't multiply two vectors together. That I think is undefined, but you can multiply a vector by a scalar and you just do each component individually, but there's no, I think, defined operation where you can multiply two vectors. I don't even know what that would mean. Somebody might know, but I don't know if it means anything or anything useful. Division, and I decided, I believe multiplication is a little bit faster on a 486. Probably should have looked that up more. So I decided, well, I'm going to do the reciprocal and cache this and just be able to do multiplication instead of division. Because it's, you know, same thing. You know, something divided by 2 is the same as multiplied by 0.5. Then we have our length, very important. It's kind of expensive though. Ooh, the square root, but it's okay. This isn't, I'm not worried about real-time speed here. Vector 3 dot, and I guess real-time speed, I mean something where you can, you know, animate it crazy fast, like 60 frames a second, you know, that kind of like real time. Our reflect ray, which allows us to keep following a ray as it hits another surface and then bounce and see, you know, where it's going after that point it hit. Here's our set mode, setting their specific registers and using this special provided int86 because we're actually compiling a 16-bit executable, so you need to use the int86 to get the mode set correctly, whether you're going to be in text mode or 13H mode. Here's our set pixel, calculating our far pointer. This is the start of the address for the array that we can set colors to, you know, eventually to draw pixels on the screen. This is the address of where you can start drawing pixels to. So I get the pointer to this beginning address, then you can calculate your offset here of where in this big array do you want to set this color to. So it might be, you know, A001, you know, after you compute this number based off the width of the screen, and a little bit of sanity checking here to make sure you don't go beyond the bounds. And there's the color index. So you set that color to your calculated position in screen, which is an array that starts at that address, and that's the special address. You may have even seen that a lot. It's the special place where when you start 13H mode, you can start writing data to. We have our initializer palette. You have to build a color palette to suit your specific application. There are standard colors that are provided for you by default, but I decided since I only have 4 spheres and I want some nice shading, I'm going to just say, take these colors, and then since I'm only using 4 colors and you have 256 colors that you can set, I can do 64 shades of each color from dark to bright to get some really nice shading. So I just loop through each color and then 64 times. I compute an index and an intensity. Use a special out P to actually activate the index for which is a color palette you're creating, I believe. And then I just set all of the different shades of the color. So I take the, you know, what base color I'm at right now. It could be green. And then I just keep multiplying it by an intensity as I work through the 64 different intensity levels, and I set them in that palette I'm creating. Then I have 4 nice palettes. Then the shade color allows me to just pass in a color like 0, 1, and then the intensity that I get from the calculate light function later of how bright the color should be. Then I calculate the index of where I should find it based on only having 64 colors. per index. And then this allows me to return the right position of the color that I'm going to call out of the palette to show on the screen, eventually go back into the, which will call back into the set pixel. And that will be the color right here. And then we have the intersect ray. And this is going to be a little bit complicated. It's solving the quadratic equation. That's how we're getting the spheres, but I'm not going to pretend that I know the math super well. I just basically converted the formula that I've seen many times, but I'm not going to derive it for you on a whiteboard and how do you produce it. I'm not really super great at math, so I can convert the math and I can find the formulas I need and I can plug in the numbers that I need. So this is basically the quadratic formula with some other nice things sprinkled in here that the author talked about in the book. That again, it's in the description. It's a free book too. I just converted to pseudocode, but this is from pseudocode to C89, strict C89. And when I say strict C89, the hard thing about C89 is you have to declare your variables at the beginning of a scope. So when you start like a new scope here, you got to define all your variables up top. You can't put them wherever you want. You could put them right here. You could put them at the beginning of there. That's a new scope, but you can't do this. This is going to be a bozo no right here. Like that'd freak it out. It's just unfortunate. It does get to be a little bit annoying, but I've managed to work around it. And sorry for these crappy variable names. I just took them from the book. I don't usually write that bad of variables names ever, but it'll kind of match up the book. If you're going through the book, you'll see, oh, there's the A, intersect ray sphere, and then closest intersection as we figured out what we're hitting. And you see the spheres, and the sphere count is passed in here along with our direction and the position of the camera, which he has O in the book. Then our list of spheres, which is 4. And then we do the intersect ray, figure out what we're hitting, how close it is that we're hitting, what point we're hitting, and what sphere we're actually hitting in the scene, sorry. And then we return that once we figure out, oh, we're hitting the green sphere, okay, or the blue sphere. And then the canvas to viewport is taking our X, Y, and allowing us to plot it to the screen and adjust for these squashed pixels. Then we got another big function here, the compute lighting, which is another kind of gnarly one, but I just, again, converted it from the pseudocode into C89, and we're just looping through all the lights, and for every light, we're computing a final intensity. So if it's an ambient light, it always gets some intensity added to this variable I. Then the point lights gets L defined here, which will be added later to the overall I intensity. And then we figure out how to cast a shadow. If we're casting a ray back up from where the pixel was hit, see if we can actually touch a light source. If it doesn't, then it must be shadow must be cast. Then we calculate the diffuse and the specular. Again, using these different formulas the book goes over for I. We've been using a power there. And then once we are finished with that, we can return the I, which is the intensity, and that will be multiplied by the color to finally give its final output of, like, say, blue, if it should be bright blue or dark blue or somewhere in between. Trace ray allows us to shoot a ray out from the screen and see where it goes, what it intersects with. Also here, when we do our closest intersection, we're trying to figure out, okay, what sphere are we hitting right now? As you know, as it scans through the screen, and like say we get here, okay, trace a ray from this pixel, go straight through. Do I hit anything? If it doesn't hit anything, we're going to get back 0, which in this case is null. I'm returning null. There was no sphere hit, so just return back full white just for the background. And if we do hit something, then we are going to compute the lighting for that sphere that we hit based off and we're going to pass in the sphere specular, all the lights, because I don't have a global for these variables, so I'm just kind of passing them into each function. I kind of try to minimize global variables. I tend to not like them. I like to have the least globals as I can, so things can't mess with state from any part of the code and cause bad problems or frustrating bugs. And then when we get the light intensity returned back from our kind of complicated compute lighting, we then take the sphere color, which maybe we hit the red sphere. We're going to take red, multiply it, say maybe it's 0.8, and then use our special shade color to allow us to find a color that's, you know, a 0.8 intensity of red, and then find it in the index. Then we return back that unsigned character that we can then send to the video, you know, video array, and have that color show up on the screen, or video buffer array. Then our main function here. So here's where our camera, I'm sorry, it's just, the book called it O, so I'm like, okay, I'll call it O. You'll recognize that. There's our, we're starting at 0, 0, 0. Here's our spheres. Got our red, green, blue, yellow, and these line up with the properties that are in the structure of sphere. And then lights the same way. We're defining an ambient, a point, a directional at different locations, intensities, and we're setting our 13H mode here. And very important to, like I said, initialize our palette after it, because I kept doing it before and getting really crazy colors, but it looks kind of, and then here's the code where we go pixel by pixel X and then Y, so every pixel on the screen. And so for every pixel, we cast a ray and see what spheres and lights see what the ray hits, and then how the light affects that ray on the final color that's produced. Then once we get all that information, color here, we say, okay, this pixel at XY is going to be that color. And it's incredible doing that, because once you do all that, you, whoops, that's not what I want to do. You get something that looks like this, which is amazing, just checking each pixel. And I decided to go left to right instead of top to bottom. You get this beautiful image here when the, ooh, looks a little crazier now. There's the spheres there. And we can even have a little bit of fun. Oh, here's our color. So instead of, let's make the green really different here. Save that. Build it. See, there we go. Now we're getting this gold ball. See, that's pretty fun. So you can change things around. We could even change the position of the spheres and see what it looks like if you move one, to show you that, you know, it's not just a fixed bitmap. Let's take the blue sphere, and instead of going over 2 to there, let's just say, just go over Pete. Okay, let's see, let's just go over 1, and we'll have it even go up. Let's see, we'll actually have it, we'll move it up the y-axis and then bring it a little bit closer in the z towards us. So we'll save that, build it, and then we should have a bluish purple sphere in a different location. And this is kind of the fun thing you can do, is experiment around. Oh, look at that. See, now it's closer and more to the left now. You can see that specular point on its top right. So it's fun to move all these things around. See that actually you can change all these. And a fun thing to do is, if you say you edit this, do it the wrong way, do it like that, which I did for a while. I couldn't figure out why none of any of my colors were showing up. And ooh, yeah, see, that's the cool color effect. It does look neat. I kind of was thinking, oh, maybe that's fine. It's pretty wacky. Not what you want. Eventually you'll get annoyed because you won't get the colors you want. But that's what I was seeing. Loopy land. And there it is. That's the code. Hope it was a decent walkthrough. I don't normally do code walkthrough, but I'll do, I think, the rasterizer next. I'll clean up that code a little bit more, get some comments in there, the same way they look now, to get that more organized, so you can do whatever you want with it. Well, I think that wraps up this video for today. Hope you had fun. Hope you download the code, run it on a computer like this, or run it through DOSBox. I think I'll make a video on how to set up DOSBox and the Open Wacom compiler, so you could easily write code like I'm doing right now without having to, you know, need this 486 DX2. You can do it for free. If you already have a computer, it's free. I'll probably eventually do a video about that, but I hope you enjoyed the review, me trying to do a code review of the stuff I've written. And I recommend you can check out the book, The Computer Graphics from Scratch. It's cool. It's free, or you can buy it. I didn't write it, but it's free, and you may learn something from it or not. Well, I hope you have a good rest of the day, and I'm going to enjoy the snowy day, because There's a lot of snow outside still where I live. And until next time,